Hi, in this video we're going to go over section 4.4 and L'Hopital's rule. So when we're doing limits in chapter 2, we didn't complete everything that we could do. We had indeterminate forms, which are the limit that cannot be really evaluated using the techniques that we presented then. This limits tends to be more interesting because there are forms that you need to do either some algebra or something else to be able to find out what they really are. These forms are what we call indeterminate forms. It includes the 0 over 0, the infinity over infinity, and many others more that we're going to show in this section. So here's how indeterminate forms shows up. If f is a continuous function at a point, then we know that the limit when x goes to a of f of x is f of a. And if we allow the limit to be evaluated by computing f of a, it works for some cases, but there are many limits that they cannot be evaluated by substitution. So for example, we have this limit when x goes to 0 of sine of x over x. Before, we kind of agree that this was 1, but if you plug 0 independently in each of the parts, you're going to get something of the shape 0 over 0. And so we need something else to deal with those limits. For that, we're going to introduce the L'Hopital's rule. L'Hopital's rule says that if f and g are two functions that are differentiable on an open interval I that contains the point a, and we have that g prime of x is different from 0 when x is different from a, then the limit when x goes to a of f of x being equals to the limit when x goes to a of g of x being 0, so pretty much giving me a form 0 over 0, implies that I can calculate the limit when x goes to a of f of x over g of x by calculating the limit when x goes to a of f prime over g prime. And then provided that that limit on the right exists, then the rule also applies if x going to a is replaced to x going to infinity or minus infinity, or a by the right or a by the left. So we can use this idea with x going to any of these options. Now, why is this true? So if f and g are not linear functions, then we replace them by the linear approximation at a equals 0. If you remember, what's happening is that when we are in a point, we can use the tangent line to approximate the function. So we can approximate the value of a function with their tangent lines. So if we're going to do this with f and g, and let's say f and g are 2 points where they're going at the same place, they're going both of them to 0. So for example, in this case, we have that g crosses at a and 0, and f crosses and a is 0, and their limits of course are 0 individually. The limit when x goes to a of f is 0, the limit when x goes to a of g is 0. Then we can approximate both of those functions by their tangent lines. So essentially, the ratio f divided by g can be approximated by f prime divided by g prime as x goes to a. And that's the reason why we can really go ahead and say, oh, okay, so by that approximation to the individual functions by their derivatives, then we can now calculate the limits by using their derivatives. So let's see some examples of that. So let's start with the most simple one, which is the one that we mentioned before. Limit when x goes to 0 of sine of x over x. Notice that indeed, if we plug 0 here and here, this is the form 0 over 0, and both of these functions are differentiable. And so by L'Hopital's rule, then we can say that this is equals to the limit when x goes to 0 of their derivative. So derivative of sine is cosine, and derivative of x is equals 1. And so this will be cosine of 0, which will be 1. And so that'll be the way that we can prove that limit when x goes to 0, sine of x over x is just 1. Now b is the limit when x goes to 1 of x cubed plus x squared minus 2x over x minus 1. And again, if you plug directly in 1, notice that this is 1 plus 1, 2, minus 2, 0. So this is also something of the shape 0 over 0. So by L'Hopital's rule, this is equals to the limit when x goes to 1 of 3x squared plus 2x minus 2 over 1. And now notice that then we're not going to have a 0 over 0 situation anymore. When I plug here in 1, then I get 3 plus 2 minus 2 over 1. And so this is just essentially 3. And that's it, we're done. Now C is one of the limits that before we were doing by doing conjugate. But now we're not going to need to do anything special of that sort. But we can use the derivative to find the limit. Notice that if we plug in 0, this again form indeterminate form 0 over 0. This is the square root of 9, which is 3. 3 minus 3, 0 over 0, 0 over 0. So by L'Hopital's rule, since the top and the bottom, they're both differentiable, we can kind of say that this is equals to the limit when x goes to 0 of 1 over 2 the square root of 9 plus 3x times 3. This is with the entire chain rule here. And then minus 0 divided by 1. So this is derivative of the top, derivative of the bottom. Now if we plug in 0, then this is going to be square root of 9 again, which is 3. So this is 1 over, there's going to be 3 over 6. 3 over 6 divided by 1. And this is just 1/2 overall. Now last but not least, we have this example here where we have limit when x goes to 0 of e to the x minus 1 over x squared. Notice that if I plug 1, then, if I plug 0, I get 1 minus 1, so 0, and below 0 as well. So I can use L'Hopital's rule. And when I use L'Hopital's here, so this is equals limit to x goes to 0 of e to the x minus 1 over 2x. Notice that if I plug in 0, this is 1. 1 minus 1 is 0. So this is also a 0 over 0 situation. 2x is also 0. And what happens is I can continue doing L'Hopital's rule. By L'Hopital's rule again, then this is going to be the limit when x goes to 0 of e to the x over 2. At this point, then this is just going to be 1/2, and then the first limit will be equals to 1/2. I could potentially continue doing this 3 or 4 times, as many times as I need, depending of the functions that I have involved. All right. So those are the first examples of L'Hopital's rules. Now we can also do the same thing with infinity. So if the indeterminate form is not 0 over 0 but infinity over infinity, we can also consider the case of the derivative, and it works pretty much equals to the 0. And notice that if something is going to infinity, 1 over that function is going to 0. So we could just potentially just flip this to be g over f in a way, or 1 over g over 1 over f in a way that they're going to 0, and then I can approximate with the tangent lines. But in reality, I can just do the same procedure and just do the same calculations, but now with the limits going to being from the shape infinity over infinity. So let me just showcase that. This is actually E here. This is limit when x goes to infinity of x cubed minus 6 squared plus 1 and 2x cubed minus 10x plus 3. This has a typo here. This is going to be an x. Notice that if I plug infinity, this is of course infinity over infinity. And so by L'Hopital's rule, then this is going to be equals to the limit when x goes to infinity of 3x squared minus 12x over 6x squared minus 10. And at this point, this is still infinity over infinity. So we can do L'Hopital's rules again. And this is going to be limit when x goes to infinity of 6x minus 12 over 12x. Again, this is still infinity over infinity. I could probably do a factorization or something if I want to here, but I can just do one more L'Hopital's here and take derivatives again. This is going to be 6 over 12, and then now this is just going to be 1/2. So finally I got to the point where I really reach a limit, and so the initial limit is going to be 1/2. Last, we have the limit when x goes to 0 of log of x over cosecant of x. So now remember that cosecant is 1 over sine. So this is going to infinity. And log of 0 is also going to infinity when we're approaching 0 by the right side. So this is indeed a form infinity over infinity. Now, if I take derivatives by L'Hopital's rules, this is going to be 1 over x, which is the derivative of log. And this is going to be minus cosecant of x, cotangent of x. And now at this point, notice that this will be 1 over x over this. So there's a couple things that I can do. If I continue making derivatives, notice that I'm going to get minus 1 over x squared. So this is still going to be a big limit. It's going to go to infinity if I continue this way. And this also will take me to infinity. So instead what I want to do, and cotangent is cosine over sine. So instead what I want to do is simply rewrite here. Here I'm not going to do L'Hopital's rules again, but I'm just going to take limit when x goes to 0 of 1 over minus x cosine of x cotangent of x. Okay? And then I can do a little bit of algebra here. Remember that cosecant is sine, 1 over sine. So essentially if I have 1 over sine here, I can flip that sign to be on the top. So now I have sine of x over x times minus 1 over cotangent of x, right? And because I have cotangent down here, I can just see this as tangent. So this is now limit sine of x over x times limit when x goes to 0 of minus tangent of x. This is going to be 1. We previously saw, and this is going to be 0. So this will be 1 times 0, and this will be 0. So notice that we're doing a combination between L'Hopital's rule and then doing some algebra to find out some special limits. So we're going to conclude for here now. In the second part of this videos, we're going to show up some other undetermined forms that we can use for L'Hopital's rule.